Hello friends, welcome to your own channel Online Physics. Here we will provide you solutions of your problems, and here we will also explain the various concepts of physics. So subscribe this channel to getting more videos on physics. So let's start this video with a beautiful quote that is, the best way to predict your future is to create it. So set your target and work until you achieved it. So in this video we will give you full explanation of 20 questions of 5 marks of CSIR-NET JRF June 2018. So watch the full video, it will help you a lot in the next coming exams. It will also give you idea about the type of questions asked in the exam and technique to solve these questions. So let's start. So now the first question of this video is, the loop shown in the figure below carries a steady current I. The magnitude of the magnetic field at the point O is. Now here this is the solution. You can see that the magnetic field B vector of half circular loop is given by mu naught I upon 2r into half, and this is for radius r. Now at radius A it will become mu naught I upon 4a, and the next is at radius 3a. Now the magnetic field at radius 3a will become mu naught I upon 12a. Now the magnitude of the magnetic field at point O is given by magnetic field at radius a minus magnetic field at radius 3a. So after subtraction we will get mu naught I upon 6a. So that is the right answer, which is option 2. Now the next question is, in the region far from a source, the time dependent electric field at point r theta phi is given as phi cap E naught omega square sin theta upon r cos omega bracket t minus r upon c. Now where omega is the angular frequency of the source, the total power radiated is. Now in this question we have to calculate the power. That is equal to integration of Poynting vector for that area. Now the Poynting vector is equal to E dot B upon mu naught. Because B is equal to E upon C, so that's why Poynting vector will become E square upon mu naught C. Now the expectation value of Poynting vector will become 1 upon 2 E naught square omega 4 upon mu naught C sin square theta upon r square. Because here cos square omega t minus r upon c will become 1 upon 2. Now we can easily calculate the power. So just put the value of Poynting vector and integrate it within that area. So after solving this integration we will get 4 pi upon 3 E naught square omega 4 upon mu naught c. So that is the right answer, which is option 2. Now the next question is, a hollow waveguide supports transverse electric modes with a dispersion relation that is k equal to 1 upon c under root omega square minus omega mn square, where omega mn is the mode frequency. The speed of the flow of electromagnetic energy at the mode frequency is. Now here the given dispersion relation is k equal to 1 upon c under root omega square minus omega mn. That is equation 1, where omega mn is the mode frequency. Now speed of the flow of EM energy is equivalent to the group velocity. So here we have to calculate the group velocity, that is equal to d omega upon dk. Now from relation 1, omega will equal to kc upon under root 1 minus omega mn upon omega whole square. Now from this the group velocity will become c under root 1 minus omega mn upon omega whole square. Now we have to calculate the group velocity at mode frequency. Now at mode frequency omega will equal to omega mn. So that will become under root c 1 minus 1, which is equal to 0. So here the group velocity will equal to 0. So that is the right answer, which is option 3. Now the next question is, the energy of a free relativistic particle is E equal to under root p square c square plus m square c4, where m is its rest mass, p is its momentum, and c is the speed of light in vacuum. Now the ratio of the group velocity Vg of a quantum mechanical wave packet to the phase velocity Vp is. Now here we have given the energy which is equal to under root p square c square plus m square c4, and here we have to calculate the ratio of group velocity and phase velocity. So now the group velocity will equal to d omega upon dk, which is also equal to dE upon dP. Now here dE upon dP equal to 1 upon 2 under root P square C square plus M square C4 into 2P C square. 2 and 2 will cancel and the relation in the denominator will equal to E. So that will become P C square upon E. And we know that phase velocity is equal to E upon P. So here put the value of phase velocity and we will get group velocity is equal to C square upon phase velocity. And it will become group velocity into phase velocity equal to C square. Now to calculate the ratio, multiply both sides by Vp square and we will get Vg upon Vp equal to C square upon Vp square. Now here just put the value of Vp, that is equal to E upon P. We will get C square P square upon E square. So that is the right answer, which is option 3. Now the next question is, in the function Pnx exponential minus x square of a real variable x, Pnx is a polynomial of degree n. The maximum number of extrema that this function can have is, now here we have given the function that is y equal to Pnx exponential minus x square. Now to find the extrema, the condition is dy upon dx equal to 0. So now take the derivative of y with respect to x and that will become Pn dash x minus 2x Pnx equal to 0. So the above equation is n plus 1th order equation. So therefore there will be maximum number of n plus 1 extrema. So the option 3 is the right answer. Now the next question is the fractional error in estimating the integral 0 to 1 x dx using Simpson's 1/3 rule using a step size 0.1 is nearest to. Now in this question we have to calculate the fractional error. So for that first we have to calculate the integral with Simpson rule and then exact value of integral and then we can calculate the fractional error. So now here you can see that the function is x and the step size is 0.1. So here you can see the value of x and y. Now calculate the estimated value of integral by using Simpson 1/3 rule. That is equal to h upon 3 sum of first and last term plus 4 into sum of odd terms and plus 2 into sum of even terms. So after calculating this we will get 0.5. So that is the value of integral by Simpson rule. So now we have to calculate the exact value of integral. Here you can see that will also equal to 0.5. Now the fractional error is equal to I exact minus I upon I exact. So that is equal to 0.5 minus 0.5 upon 0.5. So this will become 0. So here 0 is the right answer, which is option 2. Now the next question is, which of the following statement is true for a 3 into 3 real orthogonal matrix with determinant plus 1? So the options are, the modulus of each of its eigenvalues need not to be 1, but their product must be 1. The second is, at least one of its eigenvalue is plus 1. Third is, all of its eigenvalues must be real, and the last is, none of its eigenvalues need be real. Now here we have given that determinant is equal to plus 1. And the one of the property of matrix is, determinant is equal to product of the eigenvalues. So therefore possible values of eigenvalues for 3 into 3 matrix of determinant equal to plus 1 is given as, the first is 1 1 1, second is 1 minus 1 minus 1 and the third is 1 exponential iota theta exponential minus iota theta. So from these values we can say that at least one of its eigenvalues must be 1. So that means option 2 is the right answer. Now the next question is, a particle of mass m moves in a central potential that is equal to minus k upon r in an elliptical orbit, where r is equal to a 1 minus e square upon 1 plus e cos theta, where theta lies between 0 and 2 pi, and a and e denotes the semi-major axis and eccentricity respectively. If its total energy is E equal to minus k upon 2a, the maximum kinetic energy is. Now here the given values are, V is equal to minus k upon r and r is equal to a 1 minus e square upon 1 plus e cos theta, and the total energy is equal to minus k upon 2a. And here we have to calculate the maximum kinetic energy. So here we know that total energy is equal to the kinetic energy plus potential energy. So the kinetic energy will become total energy minus potential energy. Now here just put the value of E and B, and in the potential term put the value of R also. Now here we have to calculate the maximum kinetic energy. So for maximum cos theta will become 1. So here just put the value of cos theta is equal to 1, and we have maximum kinetic energy will equal to minus k upon 2a plus k upon a 1 plus e upon 1 minus e square. And now just solve this equation and we will get minus k upon 2a 1 plus e upon 1 minus e. So here minus k upon 2a is equal to e. So just put the value and we will get capital E 1 plus e upon 1 minus e. So here the option 2 is the right answer. Now the next question is the Hamiltonian of a one-dimensional system is h equal to xp square upon 2m plus half kx, where m and k are positive constants. The corresponding Euler-Lagrangian equation for the system is, now here we have given the Hamiltonian, which is equal to xp square upon 2m plus half kx. And here we have to calculate the Lagrangian equation. So for that first we have to calculate the Lagrangian. So we can calculate Lagrangian by the equation which is equal to L equal to summation of x dot p minus h. So here x dot is equal to curly h upon curly p. So now from this equation we can easily evaluate the value of p, which is equal to m x dot upon x. Now the L will equal to x dot p minus x p square upon 2m minus half kx. So as we know that Lagrangian is the function of x, x dot and t, so just put the value of p here and we will get the Lagrangian, which is equal to m x dot square upon 2x minus half kx. So the Lagrangian equation is given by d upon dt curl L upon curl x dot minus curl L upon curl x equal to 0. Now just put the value of L here and take the derivative and we will get m x double dot upon x minus m x dot into x dot upon 2x square plus 1 upon 2 k equal to 0. So now multiply above equation by 2x square and we will get 2mx x double dot minus m x dot square plus kx square equal to 0. So that is the Euler-Lagrangian equation. So option 3 is the right answer. Now the next question is the maximum intensity of solar radiation is at the wavelength 5000 angstrom and corresponds to its surface temperature, that is 10 raised to power 4 Kelvin. If the wavelength of the maximum intensity of an X-ray star is 5 angstrom, its surface temperature is of the order of, so now from Wien's displacement law, the lambda T equal to constant. So that's mean lambda of sun and temperature of sun is equal to lambda of X-ray star and temperature of X-ray star. So from this relation we can easily calculate the temperature of X-ray star. And now after putting the values we get 10 raised to power 7 Kelvin. So that is the right answer, which is option 4. Now the next question is the nth energy eigenvalue En of a one-dimensional Hamiltonian, that is equal to h equal to p square upon 2m plus lambda x4. Here lambda is greater than 0 is a constant. In the WKB approximation is proportional to, now here Hamiltonian is p square upon 2m plus lambda x4 and here the potential part is lambda x4. And now in WKB approximation, and the trick to find the relation between energy and n and the constant term in the potential part. So that is n plus half raised to power 2 alpha upon alpha plus 2 and lambda raised to power 2 upon alpha plus 2. Now here just put the value of alpha and we get the relation. And that will become En equal to n plus half raised to power 4 upon 3 and lambda raised to power 1 upon 3. So that is the right answer, which is option 1. So now the next question is the differential scattering cross section for the central potential, that is equal to beta upon r exponential minus mu r, where beta and mu are the positive constants and is calculated in the first Born approximation. Its dependence on the scattering angle theta is proportional to, now here the given value of potential is beta upon r exponential minus mu r. And here we have to find the differential scattering cross section, which is equal to f theta square. And here f theta is the amplitude, that is equal to minus 2m upon k h cut square integration 0 to infinite Vr r sin kr dr. And this can be write as f theta directly proportional to 1 upon k integration 0 to infinite, and put the value of potential beta exponential minus mu r upon r and r sin kr dr. Now here r and r will be cancelled and beta is the constant, so we can ignore it and open the sin kr in the term of exponential. Now after solving this integration, we will get f theta is directly proportional to 1 upon mu square plus k square. So now from this value, differential scattering cross section will become whole square of 1 upon mu square plus k square, and it will become mu square plus k square whole power is minus 2. And now k is directly proportional to sin theta upon 2. So here we can put the value of k, so that will become mu square plus sin square theta upon 2. Now here mu is the constant, and to match with the answer we can write it as a square plus sin square theta upon 2 raised to power minus 2. So that is the right answer, which is option 3. Now the next question is, at t equal to 0, the wave function of an otherwise free particle confined between two infinite walls at x equal to 0 and x equal to L is psi of x and t equal to 0 is equal to under root 2 upon L sin pi x upon L minus sin 3 pi x upon L. Its wave function at a later time at t equal to ml square upon 4 pi h cut is. Now here we have given the wave function at t equal to 0. And we have to find the wave function at t equal to ml square upon 4 pi h cut square. Now the given wave function is equal to first eigenstate minus third eigenstate. Now at time t it is given as phi1 exponential minus iota e1 t upon h cut minus phi3 exponential minus iota i3 t upon h cut. Now the energy in the case of free particle is En equal to n square pi square h cut square upon 2ml square. So according to this, E1 is equal to pi square h cut square upon 2ml square, and E3 is equal to 9 h cut square upon 2ml square. And the time at which we have to find the wave function is ml square upon 4 pi h cut square. Now just put these values and we will get exponential minus iota pi upon 8 bracket first eigenstate minus third eigenstate into exponential minus iota pi, and it can be written as exponential minus iota pi upon 8 first eigenstate plus third eigenstate. Now here put the value of first and third eigenstate and we will get exponential minus iota pi upon 8 under root 2 upon L sin pi x upon L plus sin 3 pi x upon L. So that is the right answer, which is option 4. Now the question number 65 is, the input Vi to the following circuit is a square wave as shown in the following figure, and which of the waveform Vo best describe the outputs. So here the given circuit diagram is the differential operation amplifier. So its waveform will be like option 2. So that is the right answer. Now the next question is, the full scale of a 3-bit digital to analog converter is 7 volt. Which of the following tables represent the output voltage of this 3-bit digital to analog converter for the given set of input bits? So now in the case of digital to analog converter, the V analog is equal to decimal equivalent into resolution. Now here the resolution can be determined by full scale voltage upon 2 raised to power n minus 1. Now here the n is 3. So it becomes 7 upon 2 raised to power 3 minus 1. And that is equal to 7 upon 7, which is equal to 1. Now here V analog is equal to decimal equivalent into resolution. So for 000 it is 0, and for 001 it is 1, and 010 it is 2, and for 011 it is 3. So that's why option 1 is the right answer. Now the question number 67 is, which of the following elementary particle processes does not conserve strangeness? Now here the first option and the first reaction is pi naught plus p, and the product is k plus plus lambda naught. So now in the first case, for pi naught it is 0, and for proton it is also 0. and in the right hand side for k plus it is 1 and for lambda it is minus 1. So that means the strangeness in the left side and right side is equal. So the change in strangeness is 0. So that means the strangeness is conserved in this case. Now in the second case, the reaction is pi minus plus p and the product is k naught plus lambda naught. Now in this case the strangeness is 0 plus 0 and in the right side it is 1 plus minus 1. So in this case the change in strangeness is also 0. So that means strangeness is conserved. Now in the third case lambda naught decay into pi naught plus n. That means strangeness is also conserved in this case. Now in the fourth option it is k naught decay into pi plus pi minus. So now in the left side it is 1 and in the right side it is 0. So that means the change in strangeness is not equal to 0. So therefore strangeness is not conserved in this case. So option 4 is the right answer. Now the question number 70 is, sodium chloride crystal is a face-centered cubic lattice with a basis consisting of Na plus and Cl minus ions separated by half the body diagonal of a unit cube. Which of the planes corresponding to the Miller indices given below will not give rise to Bragg reflections of X-rays? Now in the case of sodium chloride, the mixed state of Miller indices are absent. Now here in the third option you can see that this state is a mix of even and odd numbers. So that means this state is absent. So this will be the right answer. Now the next question is, the dispersion relation for the electrons in the conduction band of a semiconductor is given by E equal to E naught plus alpha k square, where alpha and E naught are constants. If omega c is the cyclotron resonance frequency of the conduction band electrons in a magnetic field B, the value of alpha is. Now in this question the given dispersion relation is given as E equal to E naught plus alpha k square, and here we have to find the alpha. And the another thing which is given as omega c is cyclotron resonance frequency, which is equal to EB upon m star. Here m star is the effective mass, which is equal to h cut square upon d square E upon dk square. Now here just take the double derivative of E with respect to k, which is equal to 2 alpha. Now here just put the value of effective mass, and from this relation we will get the value of alpha, which is equal to h cut square omega c upon 2 EB. So that is the right answer, which is option 4. Now the next question is the easiest question of the 5 marks. That is the value of the Landé G-factor for a fine structure level defined by the quantum numbers L equal to 1, J equal to 2 and S equal to 1. Now here the given values are L equal to 1, J equal to 2 and S equal to 1. And we have to find the Landé G-factor, which is equal to 1 plus SS plus 1 plus JJ plus 1 minus LL plus 1 upon 2JJ plus 1. Now after putting the given values of S, J and L, we will get 3 upon 2. So here 3 upon 2 is the right answer, which is option 4. Now the last question of this video is, the electronic energy level diagram of a molecule is shown in the following figure. Now here you can see the energy level diagram of a laser. Now let gamma ij denotes the decay rate for the transition from the level I to J. The molecules are optically pumped from the level 1 to 2. For the transition from level 3 to level 4 to be lasing transition, the decay rate have to satisfy. Now in the figure you can see that the level 3 is the metastable state. So that means the transition rate for this state will be very less. And after laser action, the level 4 decay very fast. So that means the decay rate for level 4-1 is very fast. So according to this information, the option 3 will be right answer. So thanks for watching. Subscribe for learning and share for helping. Share this video to all your friends so they will also get the benefit from this. And last thing, please don't forget to like this video. Thank you.